More than 2,000 years ago, a Roman geographer told a strange tale about the Mediterranean Sea. The locals would hop on a boat, travel to a specific spot 4 kilometers off the coast of Syria, and collect seawater with a funnel connected to a long tube. Then they would drink it. Amazingly, this water was fresh. 2 millennia and one Talking Heads song later, we know this story isn't complete malarkey. Scientists have discovered fresh water under the ocean in locations around the globe. But how much is there? And more importantly, can we access it? Like many discoveries throughout history, modern scientists stumbled across fresh undersea groundwater by happenstance. In the 1970s, expeditions off the coasts of Massachusetts and New Jersey were collecting sediment samples from beneath the seafloor. At the time, the prevailing assumption was that salty ocean water would completely penetrate the sediment beneath the seafloor. But in the samples they pulled up, the water was fresh. Somewhere, that Roman geographer's skeleton must have shouted, "Vindication!" Wait, what the heck is an old Jersey? But let's back up and cover some basics. The saltiness of water is often measured in units of parts per thousand. Basically, it compares the weight of dissolved salts, like sodium, chloride, magnesium, and sulfate, to the weight of water in a given volume. Seawater typically has a saltiness of about 35 parts per thousand, which our props people have approximated by dissolving 35 grams of table salt in a liter of water and handing me a sample to taste test. Okay, don't try that at home. The water found by these expeditions in the 1970s was a lot fresher than seawater, less than 3 parts per thousand, which I have also been asked to taste test. Still not great, I'm gonna be honest, but not as bad as the first one. Tastes a little like soup. Now, 3 parts per thousand is technically on the lower end of what's called brackish water. While it's 10 times fresher than the rest of the ocean, it's not quite fresh enough to drink comfortably. The U.S. Geological Survey, or USGS, considers fresh water to have less than 1 part per thousand of salt, but the World Health Organization recommends drinking water even less salty, under 0.45 parts per thousand, if you just count the sodiums and chlorides floating around. Okay, that one's not bad at all. Nicely seasoned, in fact. So with those standards out of the way, let's get back to this underwater water, which, as we've already established, isn't sitting in some lake on the bottom of the ocean. It's trapped in an aquifer beneath the seafloor. An aquifer is a bunch of sedimentary rock with lots of pore space between the grains where the water sits. In most cases, the rock above this porous sedimentary stuff is made of much finer grains, like clay, which is less permeable to water. That keeps the fresh water mostly sealed off from whatever's above it, ocean or otherwise. I say mostly because that fresh water does leak out into the ocean. This can be both a good and bad thing. While it can help carry nutrients from the land to the sea, it can also be a little too nutritious and cause algae blooms that slurp up all of the oxygen in the water. That's a big issue for animals who need that oxygen to, live. And you know who else needs aquifers to live? You. Maybe. Depending on where you are. Land-based aquifers are so abundant, nearly half of global drinking water comes from them. Humanity's been accessing the water in aquifers for thousands of years, but if you want the submarine stuff, a simple well won't cut it. Drilling into those aquifers is still super expensive, so even once modern scientists knew they existed, it took decades to learn just how widespread they really are. This revelation was partly due to a new tool called electromagnetic surveys, which involve towing an antenna behind a ship that sends out an electromagnetic field and measuring what happens to that field after it encounters different stuff. The technique was originally developed to look for oil and gas beneath the seafloor. Basically, you'd scan for an underground pocket of something with a different amount of electrical resistance than the stuff around it. But the saltier the water, the better it conducts electricity and the lower its resistance. So scientists realized they could repurpose this tech to search for underwater aquifers too. However, the resistivity of the seafloor depends on both the salinity of the water and how porous the rock is. For example, fresh water in a 60% porous rock can produce the exact same signal as brackish water in a 30% porous rock. So scientists have to make educated guesses about the rock they're dealing with and eventually drill into that rock to find out how salty the water really is. In 2019, an electromagnetic study swept across the same area that was drilled back in the 1970s, and the researchers behind it made a pretty big discovery. The old individual drill holes were not small, isolated patches of underground fresh water. They're connected, part of a massive undersea aquifer along the coast of New Jersey and Massachusetts, stretching 90 kilometers out from the coast. According to their calculations, this aquifer contains 2,800 cubic kilometers of water. That's nearly a quarter of Lake Superior and roughly 3/4 the size of the Ogallala Aquifer, the largest in North America. Parts of Ogallala could be depleted by the year 2100, so finding another aquifer that's nearly as big is an exciting discovery. Meanwhile, scientists have found evidence for offshore groundwater on most of the world's coastlines and estimate these aquifers collectively contain 1 million cubic kilometers of water. That's a third the size of Greenland's ice sheets, and could cover humanity's current global water use for a century. How did all that water get there? There are several hypotheses, but let's just cover the main two. First, if an aquifer is covered by land on one side and ocean on the other, it could have been filled by rain and snow falling on the land and seeping down through the ground to underneath the seafloor. Second, the water has just been sitting down there for tens of thousands of years. During the last ice age, the global sea level was about 125 meters lower than now. So back then, our underwater aquifers wouldn't have been underwater. They would have been beneath dry land. And like our modern land-dwelling aquifers, they filled up with fresh rain and snow. But after all that ice melted and they got covered with ocean, they just sort of sat there, waiting for human scientists to come poke at them. Which hypothesis is correct depends on the individual aquifer. Some clearly don't have any connection to rainwater, so that makes the Ice Age hypothesis more likely. And figuring out how each aquifer gets recharged with water, or if it even can get recharged, is important to know if we want to start thinking about tapping one as a resource. A rain-filled aquifer might be renewable if water flows into it fast enough, but if an aquifer needs another ice age to replenish it, we'll have some waiting to do before more water shows up. To determine which origin story is correct, scientists need to actually sample and analyze the water in a given aquifer. That brings us to the year 2025. It also brings us to Robert, better known as Liftboat Robert, the home base of an expedition that drilled into the aquifer 3 separate distances from New England's Nantucket Island. A lift boat is essentially a boat on stilts that plants itself in the seafloor, lifting the deck of the boat out of the water and creating a stable surface for drilling. Robert and company set sail in May 2025, and within weeks found fresh water with a salinity of just 1 part per thousand. The final sample. Let's give it a try. Yeah, that's great. Love it. With 50,000 liters of water pumped out of the seafloor, the researchers are analyzing the chemical composition to figure out how and when it got there. Of course, the most important question on the top of my mind is, will I ever be able to drink the underwater water? While the team aboard Liftboat Robert found stuff that isn't very salty, they still need to do a lot more analysis to figure out what else is in it. Like what kind of microbes. But the question of if we'll use these submarine aquifers as a source of water likely has more to do with economics than chemistry. Today, collecting offshore, freshened groundwater is easier said than done. The Liftboat Robert expedition cost $25 million. That's $500 per liter collected. Not exactly a bargain. If we want to extract water over the long term, we could either build something similar to an offshore oil rig in the ocean, or drill horizontally from the land. But even once we get the water, there might be even more cost to account for. Many offshore aquifers have salinities that are too high to meet human drinking water standards. And drinking water that's too salty over the long term can cause health issues like high blood pressure. So we might still need to desalinate this fresh water. But at least for now, desalination is also an expensive and energy-intensive process. One study published in 2011 looked at the cost of drilling, extracting, and desalinating water from submarine aquifers, and found it's likely the same or maybe slightly cheaper than just desalinating regular seawater. Finally, whether or not we drill into a given aquifer really depends on the location. New Jersey is a prime example of somewhere that has other, less expensive sources of water, so needing to extract anything from an offshore aquifer is unlikely in the near future. But that's not the case everywhere. Take Cape Town, South Africa, which faced an extreme water shortage between 2015 and 2018. Its nearby offshore aquifer contains enough water to sustain the city's current usage for over 13,000 years, assuming some international bottled water company doesn't get their hands on it first. In 2023, the UN forecasted that by 2030, the global demand for fresh water will exceed supply by 40%. A lot of that's due to climate change. No surprise there, really. But there's also the growing thirst of AI data centers, which need buttloads of water to keep all their electronics cool. According to one estimate, by 2027, the AI industry will use more than 4 times as much water as the entire country of Denmark. So while extracting offshore groundwater is hypothetical today, there might be a time when it comes in handy. But for the foreseeable future, we probably want to focus on preserving and protecting fresh water that doesn't require us to go all the way to the bottom of the ocean. Okay, that one was saltier than I remembered.